Modeling variation. When scientists talk about a mathematical model for a real-world phenomenon, they often mean a function that describes the dependence of one physical quantity on another. For instance, the model may describe the population of an animal species as a function of time, or the pressure of gas as a function of its volume. In this section, we study the kind of modeling that occurs frequently in the sciences called variation. The first type of variation we're going to look at is direct variation. One type of variation is called direct variation. It occurs when one quantity is a constant multiple of the other. We use a function of the form f of x equals kx to model this dependence. All right, so notice our equation there. It should remind you of one of the functions that we've studied. All right, in this situation, we have our two variables, f of x, or y, and x. And k is not a variable, it's a constant. Right? It's the relationship between the two variables. Direct variation. If the quantities x and y are related by an equation, y equals kx, for some constant k not equal to 0, we say that y varies directly as x, or y is directly proportional to x, or simply y is proportional to x. The constant k is called the constant proportionality. So if you're told that one variable is proportional to another, you'll know that you can model this variation with the equation y equals kx. And I hope you realize that this is basically a linear equation, right? Where k is the slope, and our y-intercept is the origin, 0, 0. Example 1, direct variation. During a thunderstorm, you see the lightning before you hear the thunder because light travels much faster than sound. The distance between you and the storm varies directly as the time interval between the lightning and the thunder. Suppose that the thunder from a storm 5,400 feet away takes 5 seconds to reach you. Determine the constant of proportionality and write an equation for the variation. Right? So the distance of the thunder depends upon the time. That it takes for the sound to reach you. So the distance is dependent on the time. So distance equals, k is our constant of proportionality. We don't know that yet. We're going to solve for it. And let's use t for time. All right, so d and t are variables, and k is what we're going to solve for here. All right, but we know we have some values for that show a relationship. We have the point 5, oh, and this is a, by the way. We have the point 5,400. So we can replace the d with 5,400 and replace the t with 5 and solve for what k is. All right, so if we divide, so we have 5,500 equals 5k. All we have to do is divide both sides by 5, and 1080 is equal to k. So that means that our equation is d equals 1080 t. All right, so that equation expresses the relationship between the distance of the thunder and the time. All right, so I just answered B, by the way. But let's graph it too. We'll graph it first. I may have forgot to put a graph. Either use graph paper or, in this case, and it's not ideal, but you can sketch yourself a graph. Now, this is the graph I had, so we're obviously going to need to change the scale a little bit. Let's just keep, it makes sense to keep this, each line worth 1. Okay, well, there we go. I think my orientation's off. And let's make every line equal 500. So that means every other line would be 1,000. That should fit. 1,000, 2,000, 3,000, 4,000. Yeah, 5,000. Well, yeah, pretty much fits. All right. So actually, otherwise it's going to be a really steep line. Let's make every other line. I guess we'll make that 2,000. All right, so, and this is distance. The y represents distance, and that is in feet. And this is time, and that is in seconds. All right, so we'll graph our line. All right, so for the, oh, actually, you know what? We could. I'm thinking of the 5,400 feet, not, let's keep it the way it was, I'm sorry. Not the 1,000 feet when we simplified. All right, so we can make each line worth 1,000, it's fine, or every other line worth 1,000. Or actually, let's make every line worth 200. Then I think we have a little bit more space, 200, 400, 600, 800,000. So that'll be 1,000. All right, I've decided. That's what happens when you're scaling your graph. All right, so I think that's a little easier to graph with. Let's just make every line worth 200. All right, so after 1 second, right, we're just a little bit more than 1,000. Right, so we're not at 1,100. Right, we're on a graph that's not well oriented. Come on, there we go. So we're not quite at the next 100. Next, so that'd be 200. So we're a little less than halfway. We're just going to keep that there, I guess. There we go. All right, so let's connect. So notice our line is going to go through the origin as soon as I move it there. Not bad. Not bad at all. All right, so that is, and distance can't be negative, so we're going to stay in the first quadrant. Oh my gosh. All I want to do, I'm going to have to figure out where to put things so it ends up in the place where I want it to be. So there's our equation. Notice we go through the y-intercept, or excuse me, the origin, and we have a slope of 1,080. All right, so what does that constant of proportionality mean? All right, so notice that on the x-axis is time. All right, so notice 1 second. It takes 1 second for the sound to reach your ear if the storm is 1,080 feet away. So we can explain it like that. It takes 1 second for the sound of the storm, the sound of thunder, to reach your ear. For every 1,080 feet away that the storm is. There we go. And then let's answer C here, the last portion. Boy, this orientation, I have to reorient the board. If the time interval between the lightning and thunder is now 8 seconds, how far away is the storm. All right, so we can use our equation, all right, to figure it out. All right. So C, all right, so we have D equals 1,080 T. If it's 8 seconds, we'll just substitute 8 for T. So that would give us 8,000 plus 640, so 8,640. All right, and that's how far the storm is away, right? 8,640 feet. All right, and that's, I think, our only, our next topic will be inverse, but let me just check. Yep. So we're going to end this video here. And actually, let me go on the last page so that if I pause it, you can copy some notes if you've missed them. All right, so thanks for watching. Bye for now.